What temperature are the cold regions of Minecraft? What a question. A simple question. How cold does it get in the snowy plains, the taiga, how do you say that? The frozen peaks? This is the question that sparked my imagination this week, and I thought at first, maybe like you are right now, that it is a dumb question, an easy to answer question, one that wouldn't be worth doing a video on. Little did I know that the path to answering this question was laden with trials, tribulations, sweat, blood, tears, explosions, drowning, falling, flying, and finally, after enough pain and suffering and wading through formula after formula, finally I found my answer, and it's freaking terrifying, amazing, beautiful, and disastrous. This question came to me while I was playing Minecraft. This is the game that I'm currently in, and this is the treehouse that my daughter made me build because she doesn't totally understand what I do for work and demanded that I drop everything to make a treehouse. So, since I spent like 5 hours on it, I thought I'd show it to you, and this is my treehouse that my daughter made me build. So, cold, freezing temperatures. There's actually a winter storm going on outside my window right now, and I'm fighting the urge to go sledding, so this feels strangely apropos. To get the rest of you up to speed, if you don't know, there's these things called biomes in Minecraft. Biomes are areas of the game that have unique or specific environmental qualities. Temperature, flora, fauna, trees, weather conditions, you know them even if you didn't know what they were called. You get deserts, plains, oceans, mountains, mushroom fields, swamps, and of course, all the frozen biomes. Biomes are generated using a pretty interesting set of processes. These involve Perlin noise functions, progressive scaling algorithms, and other methods to develop landmass to ocean ratios, and it makes temperature cluster zones, and then it puts biomes that fit certain criteria within those temperature zones with weighted randomness. This means the game very intentionally tries to avoid putting really cold zones right next to like desert climates. This used to happen all the time in older versions of Minecraft, but I spent about an hour looking for this in my games, and the closest I could really find snowy regions to a hot region was something like 1,000 blocks. Now that's really close if you're talking about temperature and weather, but it is nothing like the old days where having deserts right next to snowy biomes was totally the norm. My original idea for this video was to do basically the same thing as my ye oldie Zelda video about weather in Hyrule, because I am totally unoriginal and uncreative by nitpicking the temperature and water vapor gradients in the world of Minecraft, but I got focused, fixated, hooked, and tripped up on some tiny little detail that was the key to unlocking this weather mystery, and answering it took up all of my time, energy, and money, and that is this, the freezing temperature of water. See, in order to get proper estimates for just how explosive the weather in Minecraft should be, what with having snowy tundras only a kilometer away from blistering deserts, we have to know exactly how cold the cold regions are. Ideally, we'd need to know how hot the hot regions are too, because then we'd be able to get a temperature gradient map painted. Why do we need to know this? Well, because temperature is complicated. We're used to thinking of temperature and heat as the same thing, and they're not. They're related but different, and heat is actually the key problem with all this weather business in Minecraft. Temperature is a way of measuring heat, essentially, while heat is the actual energy stored within a system. Heat energy is the microscopic vibration of molecules and atoms and subatomic particles in any mass. A block of air, a block of water, it all stores heat. Now, say I take two different pots out of my cabinet. I fill one pot with exactly 1 liter of water and the other with 2. Now, I heat both pots up to a boiling temperature, 100 degrees. They're both the exact same temperature, right? However, at a specific heat of 4.186 joules per gram, meaning that it takes 4.186 joules of heat energy to raise 1 gram of water 1 degree, and assuming the water starts at 10 C, I've put 376 kilojoules of energy into the 1 liter pot, but 753 3 kilojoules of energy into the second pot with 2 liters in it, meaning that while they both have the same temperature, they both have wildly different amounts of heat energy stored within them. And this can vary tremendously from object to object and substance to substance. What we perceive as hot or cold when we touch things is actually heat energy either leaving our bodies in the case of cold or entering in the case of hot. So the heat capacity of various objects and substances and even the air plays a big part in how we perceive the world around us. Heat energy moves from objects that are different temperatures. If you put something cold next to something hot, the hot object will lose heat energy, putting it into the cold thing until they are both the same temperature and reach equilibrium. This is how water freezes. If you put liquid water outside in winter or in your freezer, it has a certain amount of heat in it, energy that's stored as vibrating molecules. They're vibrating so much that they can't settle into a crystal structure, ice, and just keep sliding over and around one another. In other words, they are a fluid, but now it's surrounded by air that's colder, a lower temperature. All that energy from the water, the heat, moves into the air, warming it up. Air has a much lower heat capacity than water, but there's usually a lot more air hanging around, so the hot particles leave or transfer that heat into nearby air particles, freeing up some energy space so it can keep pulling heat out of the water. Slowly, all that stored heat energy leaves the water. The molecules stop dancing so fast, they get tired and slow down and start to lock into place. Eventually, if the air around the water is cold enough, that is, at or below the freezing point, the water loses enough energy that it starts to crystallize and form ice. Another thing to keep in mind is that the bigger the difference in temperature, the faster heat energy is transferred. It's kind of like the more heat you shove into something compared to the world around it, the higher pressure it has. So when it releases that heat, it lets it go really fast. Alright, so you know the basics now, the very basics. Why did I go over all of this? Because you need to know why my analysis of Minecraft's weather got hitched up before I got very far. In order to know how dangerous and implausible the weather in Minecraft is, I have to know the difference in temperature from region to region, because that dictates how much energy should be moving between them and how quickly. The more and faster, the more dangerous and horrific the weather. Unfortunately, I never got that far because answering this one question was a monumentally complicated task, and it alone almost drove me crazy. Water freezes pretty fast in Minecraft, and we'll get to the details later, but without knowing certain information about the world itself, this is basically a meaningless factoid. Specifically, we need to know the air density, and if we can get our hands on it, the air pressure. This is for a couple of reasons. For one, pressure, that is the weight of the atmosphere pressing down on a fluid, has a big impact on how it changes phases. That is to say, what temperature it needs to be at to vaporize into a gas or crystallize into a solid, and this has real implications even here on Earth. If you're up in the Rocky Mountains at altitude, water boils at 90 degrees Celsius, which means cooking food up there without a pressure cooker takes more time. And why, if you chuck water into space, which basically has infinite no pressure, it will instantly boil away into vapor. This is because the weight of the atmosphere pressing down on water actually keeps its molecules from just flying out all over the place. Air literally holds water down. This is what's known as vapor pressure. And this is where I started to get into some real trouble. Air pressure, air density, how the heck are we gonna get that? I thought about using lift generated by gliding with the elytra, but the coefficient of lift proves to be a pretty major problem in figuring this out. I tried possibly using the water displaced by the boat under the gravity of the Minecraft world, but this really didn't help and I couldn't figure out how to make it work. And then I had my genius moment and it all clicked. Terminal velocity. It was the buoyancy of the boat that gave me the key, because buoyancy and terminal velocity are both related. When you're falling, in Newtonian terms, gravity is pulling you down with a force. This is the force of gravity, and it causes you to accelerate. That is, you're changing speed. Between you and the ground, however, is air, and it's gotta get out of the way, right? So as you accelerate and move, you push air molecules out of the way, another word for pushing pushing out of the way is accelerating. You are accelerating air molecules. And as per Newton's third law, for each action, there's an equal and opposite reaction. That is to say, those air molecules push back. They exert a force. This force is buoyancy. Okay, I thought I could ignore this, but the more this video went on, the more it bugged me, and I just have to correct it. Technically, this is the force of drag, which isn't exactly the same as buoyancy, which is caused by a voluminous object displacing a fluid. It's similar, and they are related and correlated, but technically not identical. Thinking about buoyancy is what got me down this thread, though, and I misspoke a little bit here, and so I just had to correct that. Back to the episode and Tanya's fantastic editing. And the faster you go, the more molecules you're pushing out of the way, and the more force is exerted on you, until the force being exerted on you matches the force of gravity, and you reach what's known as terminal velocity, your maximum fastest falling speed. We can calculate this using this formula here. Vt is terminal velocity, m is mass, g is gravity, rho is fluid density, a is the projected area of the falling object, and cd is the drag coefficient. Drag coefficient is something that we can look up, and I measured the gravity using this formula to get a value of 27 meters per second squared of gravitational force, but we have a problem. We want to know density, so we can rearrange this formula, so we're looking for the rho, but that leaves us with two unknowns, the density and the mass of the falling object, in this case, Steve or Alex. One step forward, two steps back! Well, we figured out Mario's mass using rocket science and water jets one time. Maybe we can do the same thing with the protagonist of Minecraft, so I did the only thing that made sense at the time. I blew myself up! I had to cut this section because my video was getting enormous, but suffice to say hundreds of slimes died, and all for nothing because my potential energy math put Steve and Alex's weight at over 600 tons. It was a dead end! I was back to square one. Thankfully, it turns out that square one was exactly where I needed to be today. Terminal velocity. The key to everything was, of course, terminal velocity. It was the whole time. This is where everything started to snap into place. I didn't need Steve's mass if I could eliminate all my other unknowns, and I could do this if I used another fluid aside from air to measure terminal velocity. Something consistent, something that exists in our real world, something that barely changes no matter where you put it. Lava. Nah, I'm just kidding, it's water. Water is the answer, Mandrake, and it always was. You see, while the phase water takes is highly dependent upon ambient pressure, once water is a liquid, it does not like to be compressed. It's called incompressible, even though this isn't strictly true. At the very bottom of the ocean, with the entire weight of the water above it and the air above that pressing down with huge pressures, water only compresses a very tiny bit. This means that the density of our fluid, in this case water, remains relatively consistent and is a known factor, which means we can measure the terminal velocity of Steve sinking in it. And let's be real, sinking is just falling. Then we can work backwards to get Steve's mass and then use that to remove our unknown in our other rearrangement of the terminal velocity formula to get the air density of Minecraft, and we're back in business. Steve is kind of boxy, so I used a pretty high drag coefficient of 2.1, the number for a rectangular box falling through a fluid. Steve reaches a glacial speed of 5-ish meters per second of falling speed with a density of 1,000, a liberal projected area of 1 square meter. That's an overestimate, but you'll see why I overestimated in a second, and a gravity of 27.06 meters per second squared. We can finally close the book on Steve and Alex's mass, and it comes to 9.7 kilograms. That is very small. That's like 2 of my cats put together, spread out all over this one guy. Well, I guess that's like one way we can justify this guy flying on those wings that have such a small surface area. Well, whatever. I'm gonna take it. It's a hell of a lot better than 600 tons. Taking our styrofoam protagonist mass and plugging it into this formula, given a terminal falling velocity through air of 36 meters per second, we get an air density of 0.185 kilograms per cubic meter, which is about 15% the density of Earth's atmosphere. This puts Minecraft's air pressure equivalent to something like the air pressure on Earth at 15 kilometers high, about 12.1 kilopascals. I know that's making some assumptions about gravity and atmospheric mass, but I'm just barely clinging on at this point, man. Just please let me have this. I'm just kidding. It turns out we didn't need to do any of this. I could have just looked at this phase diagram and known that the freezing temperature of water barely changes with pressure as long as our air pressure is within this massive range of 100 million pascals. Water will always want to freeze at just around 0 C. God dang it! Well, I guess we can at least confirm that the atmospheric pressure likely falls within this range, and the amount of air surrounding the water might become relevant in a bit when it comes to making judgment calls about numbers, because we ain't done yet. We have our relative air density, water density, now we need to figure out how fast the water is freezing. I built a rig for testing this that had 100 blocks freezing in it. I separated them out like this because whether they're adjacent to one another seems to impact how quickly they freeze, and I wanted to remove that from my concerns. On average, it turned out that 1 ton of water freezes in just under 2 seconds of real time, but Minecraft has an accelerated time scale where an entire day happens in 20 minutes. That's 72 times faster than the real world, which bumps our freeze time up to a respectable 133 seconds, or just over 2 minutes of time to freeze. Now, remember what I said earlier. Cooling is the movement of heat energy from a substance into another that is a lower temperature. So, in theory, knowing how much the water is cooling by and how quickly, we can figure out the air temperature. Let's give this game a fighting chance. Let's say the water is starting out pretty cold, only 10 degrees Celsius, and we want to cool it to 0. Using our formula from earlier and knowing that we have a literal ton of water here and saving ourselves the headache of considering the latent heat of fusion, we know that to cool water by 10 degrees, we would have to remove 41.86 megajoules of heat energy. This all has to happen in just 133 seconds of adjusted time. Is this possible? Maybe. Joules over time, energy over time, is measured in watts. Yep, just like electricity. Energy is energy, man, and if we know the watts, 313,000 in this case, then buddy, we are almost there. May I present to you this bad boy, the convection heat transfer formula. The key to unlocking it has been staring at us in the face the whole time. Watts of heat energy equals the convective heat transfer coefficient times the temperature difference. This formula is meant to describe the rate of heat energy transferred between two substances of different temperature, given you know the temperature difference between the two, the amount of surface area that is in contact, and a coefficient number. We know the watts. We know the area, 6 square meters, 1 for each side of the water cube. I'm being generous. We can look up the coefficients, and since we're estimating our starting water temperature, if we use this formula to find the temperature difference between the materials, we can finally figure out how cold it is outside in Minecraft with simple arithmetic. I love my job! And it's here where, believe it or not, all that work we did finding the air density finally pays off, since we know the atmosphere of Minecraft is extremely thin. When we're looking at the free convection transfer coefficients, which are pretty wide, we need to pick something on the low end to account for the thinner atmosphere and the lower mass involved. Between 0.5 watts per meter squared per Kelvin and 3000, I picked 500. It's arbitrary, but it's way on the low side to account for the lower heat capacity. Rearranging our formula so it looks like this instead to solve for temperature difference, all we have to do now is hit the equal sign on our calculator to learn that the air is 104 degrees colder in Kelvin or Celsius than our starting water temperature, which makes the tundra, frozen zones of Minecraft a balmy -90 -94 Celsius or -137 Fahrenheit. That is surprisingly believable. It's very cold, but not impossibly cold. For one, it's not below absolute zero. It is, though, colder than any naturally occurring temperature on Earth, but it's about what you would expect for a winter on Mars. And given the thinner atmosphere, well, I mean, I'm gonna call it plausible. And with higher HC coefficients, it could be even warmer. At 1000 instead of 500, you get -42 degrees, well within what's possible on Earth. Kinda freaky to know that you could put a giant cube of water outside in Antarctica and it would freeze solid in 2 minutes with zero insulation, huh? So yeah, whatever. It's impossible to have a place this cold next to a normal plain or forest, and yeah, the weather would be a nightmare of electricity and hurricane winds and constant rain and death and whatever, but you already knew Minecraft biomes were unrealistic. No, through the course of researching this video, I learned something. Something that I hope that you learn too, and that's this. With enough determination, experimentation, research, and stubbornness, you can find the answer to just about anything. That by wading head first into a puzzle, no matter how overwhelming and scary it may appear, you can eventually solve it and learn something in the process. Sometimes the journey to discovery means a lot more than the discovery itself. Anybody can put numbers into a formula, but it's how you get to that formula, how you find those numbers, the investigation, the inquisitiveness that makes the difference. And I think that might be cooler than even the temperatures in Minecraft. Sincerely, Austin. Thanks to my patrons who made this exhaustive deep dive into frozen temperatures possible, especially these high-tier folk I'm talking about. Juan Santamaria, MadLad616, Miss Kendra, Ronald Coleman, Alan Hagers, AdamTP, Nicholas Splinger, Marissa Resnick, Nick Patterson, and Loretta Mazurf. Now I have to go take a nap because this video is long.